last plenary talk, also last talk of the conference. It's a very great privilege for me to introduce MIHALIS DAFERMOS, that is very well known now new star of general relativity and also mathematical tool about cosmology. That is the subject of today. This is a very fascinating field in which we have together geometry, analysis, and mathematical physics, all overlapping each other. MIHALIS is professor in Cambridge, also in Princeton at the same moment. I don't know what is the precise situation. He received several prizes for this important result. Therefore, please, today the title of the talk is The Dynamics of Black Hole, Space-Time in General Relativity.
So thank you very much for the invitation to speak here. I hope that you can all hear me. So the title of my talk, indeed, is The Dynamics of Black Hole Spacetimes in General Relativity. I know that this subject may be slightly foreign to many of you, so I'm going to begin with a short primer on general relativity and its dynamical formulation. This will be the shortest introduction to general relativity ever. It will only be 3 slides, but I hope in those 3 slides to say everything that you'll need to know for what follows. So there's another word in the title of my talk, namely the notion of black holes. So the next thing we'll have to understand is the black hole notion, and this is exemplified by a special solution of the Einstein vacuum equations, which I will show to you, namely the Schwarzschild solution. So actually we'll spend a little bit of time trying to understand in some level of detail what is the Schwarzschild solution and in what sense this solution contains this mysterious black hole. Now, one difficulty in general relativity is that the Schwarzschild explicit solution of the governing equations does not come alone. It's contained in a larger family, which is even more bizarre than Schwarzschild itself, the Kerr family. So I will very briefly introduce to you also this Kerr family. And then we'll go to sort of one of the main sort of themes of the talk, which will contain some of the results that I want to present, namely the stability of the black hole exterior. So this is a sort of important open conjecture in the subject. It still has not been resolved, but there are some sort of results in the direction of that conjecture. And finally, I don't know, we Greeks, we always want to know the inside story. So I'll end with a discussion of the inside story. Okay. So that's the outline. Let's begin in earnest with the primer on general relativity. So very simple to say what I want to say. For the purpose of this talk, general relativity is simply the study of Ricci-flat Lorentzian 4 manifolds M, G, which satisfy the celebrated Einstein vacuum equations. So geometrically, this is just the equation that the Ricci tensor of this Lorentzian 4 metric should vanish, so Ricci G equals 0. But we all know our differential geometry, so we all know that if we write the Ricci tensor explicitly in an arbitrary coordinate system, then it's some second order nonlinear expression in the metric potential, so in the sort of components of the metric G, mi, ni. So in particular, this is actually a second order nonlinear system of PDE. And, well, slightly more difficult to see, this system is hyperbolic. Okay? So I'll return to that fact in just a second. Anytime I show you an equation, we should at least have one explicit solution that you can all ponder. So clearly the simplest solution of this equation is just Minkowski flat space. Okay, so that's R4, that's the manifold, with metric minus dt squared plus dx squared plus dy squared plus dz squared. Okay? So if you want, that type of expression is the prototype of a general Lorentzian metric. So what makes it Lorentzian is precisely this minus sign. And you should think that Lorentzian geometry is to Riemannian geometry as somehow, well, let me say it like this. Lorentzian geometry is to this expression as Riemannian geometry is to the Euclidean metric. Okay? So, of course, this is clearly an explicit solution of this equation because this metric is flat. That's to say the whole curvature tensor vanishes. And this Ricci curvature, whatever it is, it's just a trace of the full Riemann curvature tensor. So, particular, it vanishes. So, what do we need to know about Lorentzian geometry to continue? Well, we just need to know in what sense it differs from Riemannian geometry. And this is, again, very, very simple to explain. The point about Lorentzian geometry is because the metric is indefinite, there are distinguished directions just in the tangent space, and the directions are distinguished exactly by the sign of the sort of length squared. Okay? So in particular, we can partition tangent vectors into three classes. So we call the tangent vector null if its length squared is 0, but the vector is not 0. Okay? So that's what happens when you have indefinite metrics. So the set of null vectors at the point P, I'll denote it by n sub P, will call vectors time-like if the length squared, so GVV, is negative. And finally, we'll call sort of the more familiar case where the length squared is positive, we'll call these the space-like vectors. And it turns out that the set of null vectors forms a double cone in the tangent space of any point. So this is sort of the cone shaded here. And what's inside the cone, and you can make sense of that as long as the dimension is more than 2 plus 1, so 2 plus 1 or more, you can make sense of inside the cone. So what's inside the cone, these are the time-like vectors. So here's an example T. And what's anything outside the double cone, these would be the space-like vectors. Moreover, one more piece of structure that we'll always assume present. So I'll always assume that you can sort of continuously pick out a sort of top component of the cone. So that's what's known as a time orientation. So then null vectors which are on the top component of the cone, I'll call them future-directed null vectors. And similarly, time-like vectors which are sort of in the interior of the top component of the cone, I'll call them future-pointing time-like vectors. So the only other thing that maybe I should tell you, as far as terminology is concerned, is that collectively null and time-like vectors are known as causal vectors. Okay? So given sort of this structure and this time orientation, we can talk about future-directed causal vectors. Okay? And this will be essentially all we need to know about Lorentzian geometry in order to make sense of the black hole notion in a few slides down. So finally, I said there will be, I can use this. There will be 3 slides of introduction. So here's the third slide of introduction general relativity. So it turns out that the Einstein equations are naturally hyperbolic. And you should think that this is not at all unrelated to what we just saw here. There are, in particular, distinguished directions by the Lorentzian metric, and the null directions are precisely those directions which geometrically are characteristic with respect to the equation reach equals 0. So those of you who know your Riemannian geometry can contrast. In Riemannian geometry, somehow there are no distinguished directions, and the equation reach equals 0 is elliptic. Okay? So somehow these null directions are in fact precisely the characteristic directions for the equation reach equals 0. And as you would expect from any sort of hyperbolic system of equations, there is a well-posed initial value problem, and this is sort of the problem that it makes sense to study in the subject. Now, it took a long time to get this right and to get the formulation right, and this is just the 3-slide introduction, so I'm not going to go through that history. So let me just take the story at its culmination with this foundational theorem of Madame Choquet and Robert Garrosh, which says that there's a notion of initial data. So initial data in general relativity, it's maybe easier to draw things. So initial data is a 3-manifold. I'm not going to be able to draw a 3-manifold inside of a 4-manifold, which will appear in just a second. So I'm going to draw the 3-manifold as a 1-manifold, so it's a curve. Okay? So this is a 3-manifold, together with an initial Riemannian metric. Okay? and something that will represent the derivative in time of the Riemannian metric, which geometrically, those of you who know your differential geometry, it should be the second fundamental form of this in sort of the spacetime that I'll discuss in just a second. So this is an initial data set. Well, the story is complicated if you know your differential geometry. Clearly, if this is going to live in a sort of Ricci flat manifold, then these have to satisfy certain compatibility conditions that come from sort of the classical Gauss and Codazzi equations. But so let me just brush over that fact, saying satisfying some constraints, some sort of underdetermined equations. So that's what the initial data set is. And the foundational theorem is that for any, let's say, smooth initial data set, there exists a unique maximal solution of the equations. That's to say, there is a four manifold, which I'll just draw here. M comma G, which is the biggest, quote, globally hyperbolic. That's actually a notion that's due to Leray, and I'll tell you what that means later in the talk, so don't forget about it now if you want. There is a biggest globally hyperbolic solution of the Einstein vacuum equations arising from the data, and arising from the data simply means that this is a codimension one submanifold in that, and this is its induced metric, that's to say the first fundamental form, and this is its second form. Okay, so sort of you should think that this theorem, which you can think of it as the foundational theorem of general relativity, in particular allows us to discuss dynamics of general relativity. So there's an unambiguous map from initial state to solution. Okay, so somehow, without this theorem, you could not rationally entertain any question in general relativity. So there's a lot of actually recent refinements of this theorem, in particular in the context of low regularity. So those of you who went to the talk of Jérémy Seftel know that you can now prove a version of this theorem where the initial data is only assumed to be, say, the metric in H2. So that's to say the curvature tensor of G bar only is assumed to be L2. Okay? So there's still an active area of research just trying to refine this foundational theorem. And that's very important for various things. Okay, so that is the introduction to general relativity. So let's go on to understanding interesting questions about dynamics. And again, as with any physical theory that we know and love, before we really start talking about general questions of dynamics, we really have to understand some of the most important explicit solutions of the theory. So I've already told you one explicit solution, namely Minkowski space. We'll actually get back to that one later on when we talk about dynamics, but as far as its geometry, well, its geometry is, you could take a course in its geometry, but for the purpose of this talk, we'll say that its geometry is pretty simple. So I'm going to tell you what is the second simplest explicit solution of the Einstein vacuum equations. That is the celebrated Schwarzschild solution. Okay, so this is the next topic of the talk, the Schwarzschild solution, and this will lead us to the notion of black hole. So, first of all, this solution is very, very simple to find, and in fact, it was found not a month after the Einstein vacuum equations were first written down by Einstein. It was found by Karl Schwarzschild already in December 1915, in fact. It's not a single solution, it's a one-parameter family of solution. I'll call the parameter capital M. M stands for mass, but I encourage you not to think of what that means yet, or maybe ever in this talk. And, well, you can write down the solution explicitly very, very easily in local coordinates. So I told you that in general relativity, the sort of unknown is a manifold with a metric. So formally speaking, I really should first tell you what the manifold is, and then tell you what the metric is. I'm not going to do that for two reasons, partly because for historical reasons, namely when the theory was first formulated, people did not really have that geometric point of view. But moreover, exactly because it's actually much harder to find the right manifold than it is to write the right metric expression. So the metric expression formally came first, and understanding the right manifold took many, many years. So we'll sort of, in a very, very short time interval of this section of this talk, we'll go through exactly that development, and we will find the right manifold. But let me just begin with the expression in local coordinates. So here it is, coordinates r, t, theta, phi. You should think of theta and phi as spherical coordinates. You write down this expression, and if you're bored in this talk, you can happily spend the rest of it explicitly computing that the Ricci curvature of this metric is 0. Okay? So this is indeed an explicit solution of the Einstein-Blackman equations. It has lots of symmetry. So d by dt is a killing field. It's just a geometric way of saying nothing depends on t. SO3 acts by isometry. That's just a geometric way of saying that sort of there you see secretly the standard metric S2 in the theta phi part. And it's precisely because of this symmetry that this solution was found. You impose the symmetry a priori, the equation's reduced to ODE, you can explicitly solve, this pops out. Okay? So at the formal level, everything is fine. But where should this object live? What is the underlying sort of ambient manifold where this object should live? This was, in some sense, where all the confusion in general relativity lay. It's not an exaggeration to say that sort of 50 years of confusion resulted from failure to understand this correctly. And this is what will lead us to the black hole context. So in any case, we can use lots of hindsight and very quickly understand this correctly. And in some sense, most important move that we have to do, which seems so trivial in retrospect, is the following. So again, formally, let's just sort of change coordinates formally. Don't think where anything is defined. Just think of this formally. So let me introduce t bar to be this expression. Okay? Again, don't think where this is defined formally. This is sort of scratch work. Okay? So if you do that, then you can rewrite this metric. So you can rewrite this expression here in this form. So this is a sort of trivial computation with classical differentials. Okay? So, all right. So now what I'm going to do is I'm going to erase everything we did previously. I'm just going to start with this expression because I have a perfect candidate where this expression makes sense. Okay? So I'm certainly happy to consider these, so now this t bar, r, theta, and phi, as just the standard spherical coordinates on R4. Well, forget the fact that, of course, spherical coordinates are never globally regular on the sphere, but okay, we know exactly what it means to give a metric which is regular in spherical coordinates, so let's not worry about that for 1 second. So let me think of these coordinates as being coordinates on R4. And now let's consider R4 minus the r equals 0 line in R4. Okay? So this is R4 minus a line. I've taken out r equals 0, so I have r greater than 0. So I'll call this ambient manifold M plus. Okay? So it's just R4, and I've taken out the sort of, I have standard spherical coordinates r, theta, phi, t, and I take out r equals 0. Okay? So let this be our ambient manifold. On this manifold, this is a perfectly regular, fine expression that satisfies the equation Ricci equals 0. Let's call this the Schwarzschild solution. Okay. So, fine. Let's now start to study its geometry. So here is so it maybe, if you want, I can also draw this here so that I can refer to it. So I'm thinking of the board as this R4. This is r equals 0, which I've taken out so that I can define the metric. Okay? So one thing that you notice is the following. So you can look at the cylinder r equals 2m. Okay? So the cylinder separates the sort of ambient spacetime from what's inside it and what's outside. And here's the little computation that you can look at. So you can look at this function r inside the cylinder, and you can look at its gradient, okay, the gradient of r. And the miraculous thing is that the gradient of r, okay, so the gradient of r is a future-directed time-like vector when you're inside this region. Okay? So from this fact, all right, just using your classical differential geometry, then you can deduce the following statement. Suppose I have a curve, okay, that emanates from a point P such that R of P is less than 2m. Okay, so suppose I have a curve, all right, and suppose this curve is future-directed time-like. So what does it mean for a curve to be future-directed time-like? It simply means that its tangent vector at every point is a future-directed time-like vector. So it's exactly the notion that we sort of discussed at the very beginning of the talk. Okay? So suppose I have such a curve. What you can show is that if you think of R as a function of the parameter of the curve, so I call the parameter taf, okay, then the derivative with respect to taf is less than 0. Okay. So this is just a computation you do explicitly with this metric, very, very easy. Okay. So, so what does this mean? This means the following. If I'm at a point here and I follow a future-directed causal curve, then, well, R can only get smaller. So in particular, I am confined to be, again, in this region where R is less than 2m. Okay? So, so why is this significant? Well, signals in general relativity are precisely confined, signals and physical observers, to follow future-directed causal curves. Okay? They are confined by the formulation of a theory. So another way of saying this is that if I am here in this region, okay, then no signal that I send, or sort of no trajectory that me or some other physical observer or a rock that I throw or whatever, okay, can ever leave this region. So in some sense, this is the first indication that this region where R is less than or equal to 2m is special, and it's because of this property, so this will be my first somewhat naive definition, it's because of this property that I will call this region, R less than or equal to 2m, the black hole region. Okay? Because it is a region that has the property that if I'm in the region, I cannot send signals outside of the region. Okay. So a little bit of terminology. The hypersurface R equals 2m, which is the boundary of this region, I'll call it the event horizon. Okay. So that boundary is actually a null hypersurface, and we'll see this in just a second. So we actually can say a little bit more about these sort of causal curves, all right, which sort of start from a point where R is less than 2m. So if we parameterize such a curve by arc length, so now let taf not just be any parameter, let this be parameterized by arc length, okay, then it turns out that just by refining sort of the computation that gave you this inequality, you can show that in finite time with respect to arc length, R goes to 0. Okay? So what does this tell us? This tells us that this manifold M plus is geodesically incomplete. Okay? So this particular, I could take a geodesic, okay, parameterize it by arc length. This computation tells you that in finite taf time, R goes to 0, but R equals 0 is not in the manifold. Okay? So this computation tells us that this manifold is geodesically incomplete. But now you'll sort of already complain to me, and you'll say, well, okay, that's great, but I could have taken R4. Okay, this was actually, right, the manifold was R4. I delete R equals 0, but I could have considered the Minkowski metric on this manifold also. If I've taken away R equals 0, this will again be geodesically incomplete. Okay. But it turns out that whereas the answer to sort of the geodesic completeness of R4 minus R equals 0 is very simple. You shouldn't have taken out R equals 0. You should put it back in. In this case, there was a good reason why I took out R equals 0 to define the ambient manifold. And the good reason is the following. Well, if I look at the curvature along this geodesic as this time parameter goes to its maximum value, the curvature blows up. Okay. The Ricci curvature, of course, is 0. This is a vacuum spacetime, but the curvature tensor blows up, in particular the Kretschmann scalar, which is a scalar, quadratic sort of scalar in the curvature tensor, this blows up. So what this tells me is that I could not put this back in and have let's say, a C2 manifold. So R equals 0 is actually a singularity of the metric. Okay. So that's great. So that's, in some sense, the naive discussion of Schwarzschild. And you can already see naively some of the most important features, namely in what sense it has a black hole and in what sense inside the black hole there's this singularity. Okay? And you can do all these computations on your own. It's really sort of 15 more minutes. Okay? But to graduate to become a true relativist, you actually have to do this in a more sophisticated geometric way. And you see, the more sophisticated geometric way is to forget about these sort of coordinates R and T, which really are a crutch that sort of arises from the fact that we like R4 and we want to think of coordinates that are reminiscent of R4. And think about everything in coordinates that are completely natural from the point of view of geometry. And it turns out that for spherically symmetric spacetimes, there's a very, very obvious choice of such coordinates, so-called null coordinates. So what are null coordinates? Null coordinates are coordinates that I'll call U and V, for which you can write the metric in this form. So what is so great about writing the sort of metric in this form? So if I didn't have this factor minus omega squared, okay, this expression here, minus du dv, is just the Minkowski metric in 1 + 1 dimensions. Okay, so writing, let's say, in this form, then at least the metric projected to u and v is conformal to the Minkowski metric. And what's so convenient about that fact is that means that the causal structure, that's to say, the statement of which vectors are time-like, which vectors are null, and which vectors are space-like, is the same whether you're in this metric or you're in this metric where I suppress the minus omega squared. So you can read off sort of from just knowing the domain in these coordinates, the causal structure. Whereas here, I have to tell you if this vector here is time-like, space-like, or null. Okay? You have to compute it from the metric. It's not clear from the picture. So it turns out that the sort of domain of this manifold projected just to u and v, so projecting out the spherical part, in the Schwarzschild case is what I drew up there, and I'll draw it also here in real time. So you see another nice thing about, so the manifold is exactly everything. Okay, so this is, if you really want me to be very explicit, this is v equals 1, this is v equals 0. Let me call this, I don't know, u equals 0, call this u equals 1. And this is just a, I can call this point 2, 0, and this is just a horizontal line. Okay? So the domain that these coordinates map the right half plane of the RT coordinates is precisely the shaded region. Okay. So now, how does this picture help me understand the geometry of the Schwarzschild solution? Well, I have to put in some labels. So remember, R here was a coordinate. R here, you can think of it as a function on this diagram. And what does the function return? Any point here is actually a sphere upstairs, after all. So geometrically, R is just the square root of the area of that sphere. Okay? So you can think of R now as a natural geometric function on this diagram. Okay? So it turns out that this u equals 1 curve is exactly this this cylinder where r equals 2m. Okay? And you can read off this picture that this is actually a null hypersurface. Okay? Because you can understand, as I said before, what is time-like, what is null, and what is space-like, as if we were in 1 + 1 dimensional Minkowski space. And we all know from our space-time diagrams of special relativity, okay, that sort of the null directions are exactly those at 45 degrees and 135 degrees from the horizontal. Okay? So anything like this is time-like, anything like this is space-like, and these are null. Okay? So in particular, this is null. This is the black hole region, so this is the region where r is less than 2m, and this is the region where r is greater than 2m. So look at how nice these pictures are. We can read off the picture that if I start here, okay, and I go on a curve which is causal, so it's everywhere time-like or null, then, well, I'm always confined to go in a curve whose tangent is between these two directions. So in particular, I clearly can never, I'm confined precisely, in fact, to this region here. Okay. So once you get used to sort of these pictures, you can read off the fact that this is a black hole just from staring at the picture. And moreover, it's even better than this. This type of understanding of the geometry, because I've chosen these null coordinates to be bounded, it sort of endows a structure on the boundary of space-time induced by this coordinate system. So in particular, let me label the boundary by the behavior of this r function. Okay? So this boundary, which I'll talk about in just a second, corresponds to r equals 0. It's sort of funny already because it changed its direction. We'll go back to that. And this boundary here corresponds to r equals infinity. So it turns out that this boundary is extremely important in general relativity and has a name. So we label it with a script I plus, and it's called future null infinity. And you can think of this asymptotic boundary of space-time as an idealization of faraway observers in the radiation zone. Okay? So in some sense, when talking about black holes from the point of view of astrophysical observation, we live at this boundary, okay? This boundary at infinity. And somehow the correct geometric definition of black hole is that the black hole region is precisely the region that cannot communicate to this boundary. So you see, and this is something, again, that in this context you can read it off this picture. If I'm in this region here, I am confined to this region. In fact, if I start here, I'm confined again exactly here. So in particular, I can never go to this boundary. On the other hand, if I start outside r equals 2m, start here, then I can go to this boundary. Okay? So there's a sort of Lorentzian geometric notation for that. We say that the black hole region is precisely the complement of the past of future null infinity. So this is the Lorentzian geometric notation for the past of future null infinity. So this is just the set of all points that can indeed send signals to null infinity. Its complement is the black hole. Okay, anyway. No reason to play around with set theory. So there are a few more things that we can say from this wonderful picture. So the first thing I already mentioned very briefly, look at r equals 0. R equals 0, we thought, was a line. But actually, and moreover, we thought that r equals 0 was a sort of, this looks like a time-like line. It looks like it's going in the direction of time. But going to these natural geometric coordinates, we see that r equals 0 is in fact space-like. And in fact, this picture doesn't give justice to it because I'm suppressing theta and phi. R equals 0 is not in fact a line. It's actually a space-like hypersurface upstairs. So it's actually three-dimensional, whereas this thing that we took out was one-dimensional. So this picture also reveals that this singular boundary is actually a three-dimensional hypersurface, which is singular, where the metric blows up. So the singularity is much, much worse than you might have thought naively here. And in fact, not only is it true that you cannot extend the metric as a C2 metric to make sense classically of the Einstein equations, you cannot even continuously extend the metric to this boundary. So this is a very, very strong singularity. And we'll get back to this important fact later. So there's one final thing that you can see from this picture, which at first sight is very, very mysterious, but you can see it. So I told you about this boundary, and I told you about this boundary. Well, I could tell you about this boundary. That's sort of boring. This boundary here is also r equals infinity, and it's sort of what sometimes we call past null infinity. So it's really just sort of, you know, the faraway observers, but in the direction of negative time. Okay, simple enough. But I haven't told you anything about this boundary. So where was this boundary? You don't see this boundary here. Okay? I mean, r equals 0 was here. R equals infinity, okay, we all know it was infinity. Where was this boundary? So this boundary, it turns out that if you look at r is equal to 2m here also. And it turns out that this boundary, actually the metric extends to this boundary. And in fact, there's a sort of an isometry that takes this hypersurface to sort of this, and also this hypersurface to that. That's very, very mysterious. And in fact, it turns out that you can glue this region, so this manifold M+, you can glue it to just a copy of itself, which I'll call M-, smoothly, okay? So that this is just, there's an isometry relating this to that. And you get the picture that I drew there. So that's very funny. That's sort of, where was that hiding? Well, if you think about it, it's hiding in the fact that if you looked in the original picture and you followed to the past certain geodesics, then there are geodesics which to the past are also incomplete. And they don't go to this singular boundary. And they don't go to infinity. Okay? So those geodesics are exactly the ones that go into this larger space. So all that's very confusing, maybe, but it is what it is. And it's this pasted manifold that deserves to be called the Schwarzschild manifold on which the Schwarzschild metric lives. Okay? So let me just tell you one important thing about this manifold from the point of view of dynamics. So you can think of this manifold. So this picture has gotten very busy, so I'll just draw it again. So here's that funny manifold. You can think of this manifold dynamically. That's to say, I can find a Cauchy hypersurface. So I can find a 3-manifold here, which I'll call sigma. Okay? Now, this is actually a funny manifold itself, because topologically, this sigma is R cross S2, topologically. And as you go out in each of the R directions, it becomes asymptotically flat. So if I were to draw just this manifold one dimension up, I would draw something like this. Okay? So this manifold has its induced metric in second fundamental form. And Schwarzschild solution is just the unique solution of the initial value problem that comes from this manifold. Okay? So you can sort of embed Schwarzschild in this sort of dynamical picture of the theorem of Madame Choquet and Garrosh. Okay. All right. So that's great. But as I told you, unfortunately, Schwarzschild manifold does not come alone. So it turns out that the Schwarzschild solution is a one-parameter subfamily of a more complicated and less symmetric family of solutions to the Einstein vacuum equation, which are again explicit and are the famous Kerr family. So very, very briefly, so this family of solutions was only found much later than Schwarzschild. It was only found in 1963. by Roy Kerr. And its existence as an explicit solution is actually very, very mysterious. Because this is a family, so again, explicitly you can write the metric, here it is. You can spend a lot of time explicitly verifying that this is indeed Ricci flat. One of the big difficulties is the notation. But if you look at this metric, you'll see that whereas Schwarzschild was spherically symmetric and had this extra killing field d by dt, this metric only has two-dimensional Lie algebra of killing fields. So just d by dt and d by d phi. And that's not enough symmetry to sort of justify naively the fact that you can find an explicit solution. So actually hiding in this expression is a lot of hidden algebraic symmetry. And that's why it exists, and that's why it took so long to find. So I'm not going to be able to say much more about this family as I did in Schwarzschild, so I'll sort of go directly to the end of this discussion of this family. So it turns out that for this family as well, you can repeat all these considerations and you can figure out what is the manifold where it should live. And you come up with a manifold which looks like what I've drawn here. So on the one hand, this manifold is very similar to Schwarzschild. Again, there is a Cauchy hypersurface which has two asymptotically flat ends. And this is, again, you can think of it as the evolution of Cauchy data. And again, this manifold has a black hole region, because I'm labeling here, this is the future null infinity, and these are the sort of points which cannot communicate with future null infinity in the sense that I said previously. But there's a difference now. And the difference is the following. So let me draw this picture here so I can refer to it. So we're not going to need this. So this is the Cauchy hypersurface. So this is the picture here. Okay, so there's again a black hole region. Okay. But now if we look at the future boundary of this space-time, it's not space-like it was here, and singular, but it's null. And in fact, the boundary of space-time is completely regular. Moreover, you can continue the solution beyond this boundary. In fact, you can continue at C infinity as a solution of the Einstein vacuum equations. So why is this continuation not part of the solution that I drew? Why did I say I draw and this is the boundary? Well, this is precisely this notion of global hyperbolicity. If I want to think of my solution as the unique solution coming from initial data, then there has to be a global property of its characteristics. Namely, if I'm at any point and I follow a characteristic curve, let's say, to the past, I should hit initial data. And you see, if I extend it here, then I could follow a null direction like this, and I would never get to initial data. So this is why we don't allow these extensions as part of what we call the solution. This is the maximal solution of the initial value problem, and this sort of boundary is known as a Cauchy horizon. Exactly because it's a horizon for where the Cauchy problem uniquely predicts the solution. Okay, so with this introduction, I can go to the two sort of parts of the results that I want to present. The first are about the stability of the exterior, and the second about the interior story. So as I said in the very beginning, it is the initial value problem that allows us to talk about dynamics and general relativity. Okay? So this is the notion of dynamics. And having dynamics in particular allows us to rationally discuss the notion of stability. So stability means what it always should mean. That's to say, I think of a solution as coming from initial data. I wiggle the initial data ever so much. I solve the initial value problem. Does the solution of the initial value problem look like the original solution? You can think of that as orbital stability. Moreover, does it approach in time? Does it asymptote back to the original solution? You can think of that as asymptotic stability. So there's only really one context in general relativity, at least as we're understanding general relativity in the context of this talk, where such a nonlinear stability problem is known, and that is the nonlinear stability of the trivial solution Minkowski space. And this is, of course, the celebrated theorem of Christodoulou and Kleinerman from 1993, which just says exactly that in the context of the trivial solution. Think of Minkowski space as the evolution of Euclidean 3 space with 0 fundamental form, wiggle the data ever so slightly, solve the Einstein vacuum equations, look at the maximal solution. Is that close to Minkowski space? For instance, is it still geodesically complete? Maybe that's the most basic property of Minkowski space. Moreover, does it dynamically approach it in time? And the answer to both these questions is yes. So the celebrated conjecture of stability of black holes is asking precisely the same question for the Schwarzschild and Kerr family. So the question is, suppose I start with, I think of the Kerr solution as an explicit solution of the Einstein vacuum equations. I wiggle the data ever so slightly, so I take nearby sort of initial data, and I solve the Einstein vacuum equations. What does the solution look like? So in particular, the most basic question is, does it still have a black hole? So is it still the case that there's this boundary, far away observers, which I'll call future null infinity, such that if I look at the past of future null infinity, so that's this region here, okay, there's more of the space-time. All right, that says that the black hole notion is stable. Near enough space-times again have black holes. Moreover, is it the case that if I look asymptotically outside the black hole, the solution will reapproach the Kerr family? Now, one sort of comment that will be very familiar to people doing quasi-linear equations, quasi-linear wave equations, stability problems for them, for equations which are supercritical with respect to natural scaling properties, like the Einstein equations, is that to prove any sort of stability statement, you actually have to prove asymptotic stability. You cannot just prove orbital stability, exactly because the way you prove stability is through dispersion. And one of the unpleasant features of that means you can't really focus on the simpler case of Schwarzschild. You have to do the general Kerr family, precisely because even if you wiggle Schwarzschild ever so slightly, you will dynamically approach another member of the Kerr family. Okay. So this is the conjecture. All right. So let me just say very briefly about this that some of the major difficulties of this problem, they are already present at the linearized level. So suppose you linearize the Einstein equations on this background. Suppose you linearize the Einstein equations around this background. Already this problem is something which is difficult. And the study of this linear problem goes back to the physics literature, in particular to sort of foundational work of Reggie Wheeler and many other people since then. So just linearized Einstein equations on this background. And then there's an even easier problem you can ask, which is, okay, linearized Einstein equations are some hyperbolic system, which is very complicated. Let's look at an easier problem. I just look at the scalar wave equation on this background. So you can think of this as a poor man's version of the linear problem, where I suppress sort of the tensorial difficulties. I just look at the scalar wave. And just the study of this problem on Schwarzschild and Kerr exterior backgrounds, so the area outside of the black hole, has been very, very active in the last 10 years. So where are we all on this conjecture? Well, so the good news is that, first of all, the poor man's linear problem is completely understood now. So in particular, if you look at the scalar wave equation on a Kerr exterior background, in the full range of parameters of the Kerr solution, one can understand precisely the dispersive properties of the scalar wave in the exterior region. Okay? So you should really think of this as sort of a step 0 if you want to be able eventually to understand the number. And so this sort of final resolution of this is joint work with Igor Rodnyansky and Yakov Schlapp and Toporov. Moreover, very recently, we have been able to understand the true linearized problem, that's to say not the poor man's problem, the true linearized problem, but only in the Schwarzschild case. Okay? So this is sort of joint work with Gustav Holzhegel and again Igor Rodnyansky. So in particular, we can show that in the Schwarzschild case, if you look at linearized gravity, which is a complicated system of equations you get by linearizing equations Ricci equals 0 around Schwarzschild, you can understand completely the dispersive properties, so decay of these equations in the region outside. Okay, so very, very quickly, I won't take 5 minutes. I'll skip. So I was going to tell you a little bit about sort of the geometric features of the exterior of the black hole that enter in sort of the proofs of these theorems very, very briefly, just to give you a taste, but I'll skip that completely and leave you with a few words about the inside story, because we all want to know the inside story. So everything I said in this talk, or in what I talked about stability, concerned the exterior region of the black hole. Okay? What goes on outside the black hole. And what the conjecture is that the region outside the black hole is stable. So what happens inside the black hole? So let's again compare very briefly the Schwarzschild and the Kerr spacetimes from the perspective of observers who go inside the black hole. Okay? So this is Schwarzschild. Gamma, this is a time-like geodesic, aka an observer, that enters the black hole. And we already said exactly what happens to Gamma. In finite time, once he's entered the black hole, then in finite time, he will reach this singular boundary r equals 0. And this boundary is very, very singular. Remember, the metric does not extend there even continuously. And what that means is that this observer is, in fact, torn apart by infinite tidal forces. So he's torn to pieces. Okay, that's just great. What happens in the Kerr case? Well, we just saw, in some sense, so here is observer Gamma. So in finite time, he enters the black hole. And then in finite time, he reaches this boundary, CH+. But this boundary is completely smooth. There's nothing wrong with this boundary. Okay? So in principle, he could continue to live another day in some extension spacetime. The only thing is that this extension spacetime is not determined from initial data, because he's crossed the Cauchy horizon. So what happens to this observer Gamma? So you might think that this situation here in Kerr is highly preferable to situation in Schwarzschild. Because in Schwarzschild, I told you what happens to Gamma. He's torn to pieces. Whereas in Kerr, he lives another day in an extension spacetime. So it's certainly more preferable for observer Gamma himself or herself. But from the point of view of physical theory, you see, physical theory is sort of like bureaucracy. And in bureaucracy, what's important is everyone is accounted for. So in the Schwarzschild case, everyone is accounted for. Observers, they either live forever, they don't enter the black hole, and they live forever, or they enter the black hole in finite time, and they're torn to pieces, and everyone is accounted for. The physical theory predicts what happens to everybody. In the Kerr case, this observer Gamma is not accounted for by theory. And just like bureaucracy wouldn't like that, neither does physical theory. So because this is, in some sense, philosophically very problematic for the theory, one way to get around this, or to hope to get around this, was provided by Penrose, motivated exactly by the behavior in Kerr. And his hope is that what happens in Kerr is a fluke. That's to say that the Kerr situation is unstable. And for generic initial data of the Einstein vacuum equations, then the situation is more like Schwarzschild. In particular, the spacetime should, for generic initial data, be inextendable. Okay? So you can think of this colloquially as saying that generically, you have global uniqueness. Okay? So the future is determined by the present. So, and of course, if this is true, then Kerr, which conjecturally is stable in its exterior, should be unstable in its interior. So, okay, we've all read our Marx. We know the poverty of philosophy, so you wouldn't want this expectation to be based solely on philosophy. And indeed, there's sort of a better reason for hoping that this is true than pure philosophy. And this was, again, discovered by Penrose, and in fact, this is how he sort of was able to make this conjecture. And this is the celebrated blue shift effect. And very easy to explain this in terms of observers. So imagine you have two observers, A and B. So A is very conservative, and A stays outside of the black hole for all time. There's A. So A lives forever. B is the more sort of revolutionary one. B enters the black hole and heads straight for the Cauchy horizon. So there's B. So suppose A sends a signal to B at constant frequency as A measures the signal. And think about what frequency is the signal received by B. Well, because the time intervals between the crests of A, these are constant, because A's time is infinite. It's hard to see in the picture. But B's time is finite, which means that the time intervals between the crests goes to 0, which means that the frequency of the signal goes to infinity. Well, this is sort of you can think of this as an instability mechanism at the level of geometric optics. So you might think that, any sort of, once you have a dynamic degree of freedom, like you get in the Einstein vacuum equations, which are wave equations, that this should sort of be seen there. So motivated by this, he conjectured the statement of cosmic censorship. And in fact, he said something more. You see, the Einstein equations are, of course, nonlinear. So what happens in a nonlinear theory when sort of linear perturbations start growing? Well, after a certain threshold, you might expect that purely nonlinear effects should take hold. And whereas, okay, in linear theory, the best you can expect is that asymptotically you have blow-up. For the nonlinear theory, then it's reasonable to expect that you'll have blow-up now in finite time. And somehow the situation should go back to the Schwarzschild picture. So this is what I'll call very strong cosmic censorship. And this is, in fact, the formulation of strong cosmic censorship, which is mostly given. So very strong cosmic censorship says that for generic initial data for the Einstein vacuum equations, not only is the space-time future inextendable, but it's future inextendable just like Schwarzschild was. That's to say, you have a very strong space-like singularity through which the metric is not extendable even continuously, and all observers are torn to pieces. Okay. So there's been a lot of debate in the sort of community as to whether this very strong form of strong cosmic censorship should be true or not. So on the one hand, see, in physics, there's always a more ambitious conjecture to sort of trump any conjecture that you give. So there's an even more ambitious conjecture than the very strong formulation of strong cosmic censorship, which is known as the BKL conjecture. And this sort of BKL conjecture supposedly gives a very, very precise description of the generic profile of singularities in the Einstein equations. And lots of things have been written about this conjecture. And part 0 of this conjecture says that singularity should be space-like. So for this reason, almost everyone in the community sort of has had an aesthetic preference to this picture. On the other hand, there's sort of a spherically symmetric toy model that had been studied by various people. And the sort of toy model, which was very special, suggested that, so the toy model was spherically symmetric and it was a very special situation. The toy model suggested that you'd still get this picture when you perturb, but that generically this boundary itself would be singular. But it would be singular in a weaker sense than this. So people typically didn't believe this because this is a very sort of naive toy model. And sort of this is something which sort of really was the guiding idea in the field. Okay, so I will finish by announcing a theorem, which is joined with Jonathan Luke, which completely resolves this question, this conjecture of very strong cosmic censorship, given a positive resolution of the exterior stability conjecture. So the theorem simply says the following. Suppose I've solved the stability of Kerr in the exterior. So I know everything about the outside, so I'll erase the outside, and I'll just keep the statement that on the boundary of the black hole, which is this event horizon, my space-time approaches Kerr at a suitably fast rate. Okay? Exactly the rate that you expect from a positive solution of that conjecture. So the statement of the theorem is that the rest of the space-time looks like this. It looks like this. So in particular, the boundary of space-time is always null. It's not space-like. And moreover, the space-time is still extendable beyond this boundary as a space-time with continuous metric. So in particular, as a corollary of this, if indeed we have stability of the exterior of Kerr, then very strong cosmic censorship is false. So that expectation is false, and thus sort of the stronger conjectures that led to it, like BKL, are false. All right. So the problem which remains to be done, besides proving this stability of the exterior, is understanding, is this boundary singular in some sense, in some weaker sense? Okay? And the proof and some parallel work of Jonathan Luke suggests that it may still be the case that generically the Christoffel symbols fail to be square integrable at the boundary. And that statement is important because it means that even though there are extensions with continuous metric, there are no extensions as weak solutions of the Einstein factor. So this sort of revised version of strong cosmic censorship would still give you a little bit of determinism. Observers could still get away without being torn to pieces, but there would be no way of making sense of the Einstein equations. All right, well, I apologize for going a bit over. That's the end of the talk. Thanks.
Okay, thank you very much for so beautiful, well-prepared talk. Therefore, we have some question, comment. It wasn't too much clear. Okay, thank you again.
Thanks.
Yes,
Okay. I just want to announce that the 16th International Conference of Hyperbolic Problems will be in Aachen in 2016. And let's see. Oops. Bye.
Aachen, the city of Charlemagne, in the heart of Europe, where world-class research is shaping our future, welcomes you. With international flair, 2,000 years of history, a rich culture, beautiful surroundings, and with people who know how to enjoy life. Aachen, the most westerly city in Germany, is right in the middle of Europe. One step crosses the border of 3 countries. It is 1 hour to Brussels, 3 hours to Paris, and 4 hours to London. Europe grows from here. Aachen, under Charlemagne, was the first capital with European character. The Aachen Cathedral, Charlemagne's palace chapel, was the first German structure to be listed by UNESCO as a World Heritage Site. The Gothic Town Hall. 32 kings were crowned in the cathedral, celebrating their coronation banquet here. Since 1950, the city has awarded the International Karls Prize. Every year, this prestigious award for political and cultural achievements brings royals, politicians, scientists, and other religious and spiritual leaders to Aachen from all over the world.
It will be a bigger Europe than Charlemagne ever dared dream.
Knowledge creates tomorrow's competitive edge. Aachen's Technical University is one of Germany's elite universities and enjoys a world-class reputation of excellence. And Aachen's University of Applied Sciences is one of the largest and most important in Germany. The products of tomorrow are invented here today. Many international companies have therefore moved manufacturing plants and research laboratories to the region. Interdisciplinary research is a trademark of the RWTH. Quality of life. Aachen has it. Unmistakable is the ambiance of the city. With its historical old town and its 40,000 students from many nations. Take a stroll through the shops. Pause in the picturesque old town. On warm, sunny days, enjoy the almost Mediterranean flair of the city. The people of Aachen are sociable. True to the motto that commerce also takes place at the pub, Aachen has not only developed a legendary pub culture, but also has a wide variety of restaurants to satisfy every appetite. This is also true of its cultural offerings. In summer, open-air concerts attract visitors to Aachen's most beautiful squares. World-class orchestras and choirs can be heard at the Eurogress and in the Aachen Cathedral. Aachen welcomes you. Aachen, the city of Charlemagne, in the heart of Europe.